At 2:47 a.m., the night over Crimea broke without a sound. A small Ukrainian drone team pushed toward Mount Ai-Petri, the air defense brain that guards the peninsula's southwest gate. On that peak sit systems Russia trusts most: S-400 launchers, Nebo early warning arrays, Podlyot K-1 low-altitude radars, and a Panzer S-1 on watch. What came next wasn't about bigger missiles or louder blasts. It was about seconds, angles, and price. On screens meant to spot cruise missiles from far away, tiny shapes began to appear and vanish like static. A geometry glitch opened where no one expected it, and a cheap swarm started to test a very expensive shield. Pilots scrambled. Guns lit the dark. Domes that look unbreakable stood in the crosshairs, while radios filled with questions no one could answer fast enough. If a gap exists in a fortress built for the sky, what happens when the attack hugs the sea? Stay with us as we break down the tactics, the tech, and the cost math behind this strike, and what it means for the next one. Like, share, and subscribe to Military Force so you don't miss the frontline truth. Ai-Petri is the brain of a layered shield, and that shield starts with altitude but ends with angles. On the summit sit 3 key radars with different jobs. Nebo SVU watches far and high, 96L6E scans the middle bands, and Podlyot K-1 hunts low flyers near the terrain. A Panzer S-1 battery stands close as the last guard, while S-400 launchers wait for clean tracks from the sensors. This design offers long reach and fast queuing, yet it also builds a weakness that has nothing to do with the age of the hardware and everything to do with geometry, which is where the story turns. High ground extends line of sight over the sea, but radars cannot point below a fixed depression angle, and cliffs add a steep drop right in front of the antennas. That geometry creates a coastal blind strip where anything flying very low can hide under the beam. Within the first few nautical miles, targets under tens of meters ride the curve of the Earth and the slope of the mountain at the same time, so they sit below the radar's horizon for several seconds or even minutes depending on speed. Engineers know this limit and plan overlaps, yet overlaps fail if adjacent sensors share the same elevation and angle set, which means the gap can persist across the whole sector, and that is the first path an attacker will test. Sensor fusion helps, but software filters can widen the gap when the sea is noisy. Coastal radars often suppress slow surface tracks to cut clutter from fishing boats, and they deprioritize very low, very small returns that look like wave spikes. If those rules run at the same time, the system sees less and less of small objects that hug the surface, even when several sensors are alive. At night or in haze, EO/IR cameras lose range, so the backup eyes that should fill the radar gap also shrink. And that pushes the whole network to depend on tracks that appear late, which is exactly when timing starts to break. Topology also shapes where interceptors can stand. A Panzer placed on a terrace below the summit may face terrain masking to the seaward side, while a unit on the crest fights steep angles that shorten the engagement lane. When a target pops up from the blind strip, the window to classify, assign, and fire is tight because the object is already close and still low. Time to arm constraints for some missiles and the need to confirm friend or foe add seconds that the gun crew does not own, which means the first look can also be the last, and that is a poor place to make hard shots. The layout still carries strong advantages. Altitude gives early warning against high flyers, VHF bands give counter-stealth reach, and the mid-band net ties launchers to targets with efficient handoffs. Yet any fortress built for long-range raids must also defend the short-range seam where physics undercuts theory. Mitigation is clear and feasible. Place gap filler radars on lower masts near the shore, stand up EO/IR pickets at beach level, retune filters that hide slow movers, and pair the mountain sensors with ship or aerostat coverage to bend the beam downward. If those steps arrive fast, the blind strip narrows. If they lag, The close-in fight decides the outcome, which leads directly to how the interceptors struggled under pressure. Panzer S-1 lost the fight because the target set was tiny, low, and slow, which breaks the math that the system depends on. The drones kept radar cross-section extremely small, so returns hovered near the noise floor, while flight at roughly 50 meters across the beam produced a Doppler notch that looked like ground clutter. Sea reflections then stacked on top, so the tracker blended real echoes with mirror images and tried to steer weapons into empty water. By the time operators confirmed a valid plot, the range had collapsed, and geometry favored the intruder. That is why a modern turret can still miss a near object, and it sets up the timing problem that follows. Timing killed the intercept chain because the engagement lane was short and the checklist was long. The crew had to classify, deconflict friend or foe, choose missile or gun, and hand off aim points while the target closed fast at highway speeds. Several Panzer missiles need a time-to-arm distance that eats precious seconds, and those seconds vanish when a drone appears close to the shoreline. If the first shot leaves late, the seeker works with poor look angles, and a small course tweak by the drone turns a good lead into a clean miss. With the clock already against them, gunners faced a second problem that belongs to ballistics, which is where the 30mm came in. The 30mm cannons drew perfect lines in the night, yet the firing solution assumed the target would keep flying straight. The FPV pilots inserted small jinks every couple of seconds, just a few meters, so a 1-kilometer shot fell wide by a full car length. Tracer burn gave the drones free feedback, since every burst showed where calculations aimed, and the operator only needed to offset by a step to stay alive. Guns can win if the cue is early and the angle is clean, but neither condition exists over dark water with glare and spray. Because guns could not settle the fight, the crew leaned harder on sensors, which is where software choices mattered most. Filters that cut clutter also cut awareness when the clutter looks like the threat. Many coastal sets suppress slow surface returns and downweight very low tracks, so the system hides fishing boats and wave spikes, but also hides USV-launched drones that ride the same profile. Fusion logic demands steady updates from multiple sensors, yet low-altitude echoes flicker, so the computer resets confidence and never builds a firm track file. The operator then faces a screen that blinks targets on one sweep, off the next, which delays weapon release and burns more of the window. Once fusion lags, the battery cannot hand a stable cue to shooters, which explains the final failure of the loop. Cost also worked against the defender because each shot was expensive while each drone was cheap. Firing several missiles plus hundreds of rounds to chase a handful of quadcopters drains stocks and exposes reload gaps, and those gaps attract a second wave. A defender can flip the cost curve by adding EO/IR pickets at beach level, lowering masts, tweaking filter rules, and pairing Panzer with gap filler radars that look down into the seam. Until those fixes stand in place, the same target set will recreate the same engagement math and the same poor odds. And that leads straight to how the attackers exploited the blind strip with offshore relays to hit the radars behind the shield. Ukraine turned the nearshore gap into a highway by using unmanned surface vessels as floating bases and radio relays. Each USV cruised 10 to 20 kilometers off the Crimea coast at modest speed, matching normal boat traffic so radar filters treated it like background. Low-profile hulls and short wakes kept signatures quiet, while the mountain radars looked over them due to depression angle limits. From that position, the crew could launch FPV drones and keep crisp control links with little delay. With the platform hidden by geometry and behavior, the air picture began to break at its thinnest seam, which is why the relay concept mattered so much. The control chain was simple, yet clever, and simple is often strongest under pressure. Operators stayed far from danger, sending encrypted commands over long-range data links to the USV, which then rebroadcast guidance to nearby drones. Tall masts, and clean line of sight at sea level reduced static, while short hops cut latency to fractions of a second. Video came back the same route, giving pilots real-time sight to steer around fire and pick angles on sensor domes. Because the boat sat inside the blind strip, signal quality stayed stable at the moment defenders most needed it to drop, which shaped the rest of the engagement. Launch geometry amplified the effect, since starting close and low trims the defender's timeline. A drone fired from a pier must cross many kilometers under watch, but a drone fired from a SUV appears already near and already low. That shift erases early cues, squeezes time to classify, and leaves Panzer crews with only a brief lane for shots. When several boats release small swarms on staggered headings, tracks scatter like birds, so fusion software delays promotion to firm targets. Every second lost at the front of the timeline becomes a clean approach at the back end, which is how the attackers reached sensitive antennas intact. USVS also solved the power and payload problem for small airframes. Deck racks carried extra batteries, warheads, and spare airframes, so teams could cycle launches without returning to shore. A relay node can host high-gain antennas and better processors than a single drone, turning the boat into a floating cell tower for the pocket air force around it. If jamming rises, the node shifts frequency bands or moves a few cables lengths to restore a clear path. Because the logistics ride on the water and not on a single quadcopter, the swarm keeps its rhythm even as individual units fall, which sustains pressure long enough to crack hard targets. Deception finished the picture, since the best stealth was to look ordinary. Coastal radars often ignore slow vessels to cut clutter, and transponders can mimic harmless traffic patterns that do not trigger alerts. Running at civilian speeds below common filter thresholds, the USVs blended with fishing fleets and service boats, and that choice turned software rules into an unintentional shield. Only dedicated EO/IR pickets at beach level or low-mounted gap filler radars would consistently catch such shapes hugging the surface. Until those eyes appear in numbers, a handful of relay boats can reopen the blind strip on any calm night, which sets up the strikes on the radars behind the crest. The strike focused on the radars that feed the whole shield, and the first hit landed on the 96L6E. This set acts like the traffic controller for medium-altitude threats, since it builds clean tracks and passes them to S-400 launchers. Footage showed blasts on the dome and antenna face, and flame inside the array bay, which points to damaged feed networks and burned modules. When those parts fail, the set cannot keep stable plots or share queues with fire control units. With the 96L6E staggered, the network lost the smooth handoffs that keep shooters on target, which opened space for deeper hits. The second blow went to the Nebo complex, and that choice hurt long-range warning. Nebo's VHF bands watch far and look for stealthy shapes, so they give early notice against aircraft and large drones. Images showed punctures in the cover, then secondary sparks along cabling, which fits as shaped charge jet-cutting waveguides and power lines. A cut there forces current into paths that should never carry it, so boards short and racks die in sequence. With Nebo dim or blind, the sector could not paint distant tracks in time, and that delay pushed pressure onto the last low-altitude layer. The third target was Podliot K1, the set that guards the deck just above the sea. Its job is to see low flyers that hug the surface, yet a hit on the emitter or receiver chain breaks that watch. Clips showed smoke from the pedestal and fragments around the hood, which suggests antenna damage plus overheated transmit modules. Once those parts go cold, cues for low-level threats fade, and the system cannot promote tiny returns into firm targets. With Podliot weakened, the coastal blind strip widened again, and that gap shaped what happened to nearby forces on the water. A fast boat then appeared in thermal view, and a BK-16 took the punishment. The crew fired deck guns and rifles, Yet their navigation radar only showed dots without a firing solution, so they shot by eye. An FPV ran a straight profile into the bow, and the feed cut as the charge went off, which matches a clean terminal hit. A loss like that matters, because patrol craft help call tracks and act as close-range pickets for beach sectors. With one hull out and others pinned by noise, the shoreline lost another layer of awareness, and the hill became the main stage again. The damage tally showed at least 2 domes torn open and several antenna faces scarred, and the pattern tells a clear story. Take out the medium-band traffic cop, punch the long-range early look, and blind the low-altitude tripwire, and the shooters cannot see or sort. Thermal clips and daylight frames lined up with this sequence, while radio chatter hinted at frustrated handoffs and late locks. Even partial kills forced shutdowns, since crews must power down sets that show arcing or unstable loads. With eyes dulled across bands and heights, the shield lost depth and timing at once, which set the stage for the cost shock that followed. The loss of Nebo at long range and Podliot K1 at low level cut the S-400's eyesight, so detection and handoff fell sharply on the southwest arc of Crimea. Track quality dropped first, then engagement timing slipped, because shooters received late and shaky cues. Crews could still see medium-altitude targets through surviving sets, yet the chain no longer formed a clean picture across bands. In that gap, small drones and sea-skimming routes gained freedom of movement for minutes that mattered. This is why a local breach at Ai-Petri turned into a regional warning for every radar ring on the coast. Coverage gaps forced commanders to reshuffle assets near Sevastopol, which kept some warning but at a price in depth. Reserve radars can backfill sectors, however shifting them creates thin spots elsewhere, and cable runs or power links limit where units can sit. Mobile launchers remain dangerous, yet missiles without early tracks waste range and endurance. When a battery waits for a firm plot, the window to fire shrinks, and low flyers cross the line before guidance stabilizes. A network designed for reach then spends precious seconds acting local, which is the worst trade an air defense commander can make. Sustainment pressure followed fast because cost curves ran in opposite directions. An FPV or USV airframe can cost tens of thousands of dollars, while a single interceptor or a fresh radar module runs into 6 or 7 figures. Burning 2 or 3 missiles plus hundreds of 30mm rounds to stop a small swarm tilts cost per kill toward the attacker. Reload drills also expose downtime, as crews move trucks, lift crates, and clear hot barrels, and those minutes invite a second wave. When the defender spends more each minute than the striker spends each hour, tempo becomes a budget problem, not just a tactical one. Logistics then shape strategy, because spare parts and trained technicians are finite. Replacing VHF arrays, feed horns, or transmit modules needs cranes, calibration tools, and calm weather on a mountain road. Even partial damage can force shutdowns, since arcing risks total failure, so operators power down sets that still look intact. During repair windows, patrol craft and helicopters must act as pickets, yet they consume fuel and spread thin over long shorelines. If these stopgaps hold, Russia buys time. If they slip under repeated pressure, the same blind seam will reopen during the next clear night. Mitigation is possible, but it must match the threat's scale and price. Gap filler radars on lower masts can look down into the seam, EO/IR posts. At beach level can spot tiny shapes, and filter rules can stop hiding slow vessels. Paired with aerostats or shipborne sensors, the mountain nodes can regain a clean vertical stack, and software can raise low tracks faster. Only a layered fix that is cheap to run can close the budget gap as well as the geometry gap. Until those measures stand in numbers, the attacker holds the initiative, which leads directly to the question of how soon the ring can be rebuilt, and at what cost. The lesson at Ai-Petri is simple and sharp. Geometry, algorithms, and cost can break a high-tech shield when the attacker owns seconds, meters, and angles. Low routes, smart relays, and precise timing turned an expensive network into a set of late warnings, while cheap airframes hit sensitive nodes and stole the initiative. This is not only a tactical story but a budget story, because every delayed track forces harder shots and every hard shot burns money and time. When warning shrinks and reloads grow, commanders lose options before the first briefing ends, so the advantage tilts toward the side that spends less to keep pressure steady. That is where the next phase begins. The near-term test is whether the defense closes its seam faster than the offense reopens it, and the signs will be visible. Watch for gap filler radars on lower masts, EO/IR pickets placed at beach level, and filter rules tuned to stop hiding slow vessels, since those moves push eyes back into the blind strip. Track the density of Podliot-class coverage around the southwest arc and the rate of USV detection offshore, because more catches and earlier cues mean the window is closing. Look for shipborne or aerostat sensors working with mountain nodes, since a clean vertical stack restores timing across bands and raises the cost for small swarms. If these indicators firm up, the shield regains depth. If they lag, repeat strikes remain the most likely path, and the map will feel that rhythm first. From here, the balance turns on who adapts cheap and fast, not who buys big and slow. For clear maps, straight numbers, and field-level breakdowns without noise, like this video, share it with a friend, and subscribe to Military Force.